this evening, we are so pleased to be able to welcome Professor Paul Shellard as our speaker, and he's going to be speaking on the beginning of all things, modern perspectives from Lemaître to Hawking. And let me just introduce Paul briefly for you before we start. So Paul is Professor of Cosmology at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. After completing his PhD, he held research fellowships at Trinity College and MIT before taking up faculty position in Cambridge. Paul's research endeavours to advance the confrontation between mathematical theories of the early universe and observational cosmology. His current interests focus on the properties of the cosmic microwave background, the radiation left over from the Big Bang, and on primordial gravitational waves. He's director of the Stephen Hawking Centre for Theoretical Cosmology and of the Cambridge Centre for Doctoral Training in Data-Intensive Science. He also has a keen interest in the public understanding of science, most recently coordinating the Universe Unravelled documentary series for the Discovery Plus streaming platform. So Paul, really looking forward to your lecture. Thank you so much for being with us. Over to you.
Well, I'm very grateful for the kind invitation of the Faraday Institute to give one of its termly lectures. And the aim of this talk is to consider our current understanding of the beginning of the universe and what it might tell us about the big questions about our existence, and indeed what it might say about the relationship between science and religion. As a springboard for this discussion, I want to consider two contrasting perspectives on the Big Bang theory from two of the greatest cosmologists of the 20th century, George Lemaître and Stephen Hawking. And I want to then highlight how our understanding of the origin of the universe continues to improve quantitatively with the latest observations, and now going beyond the Planck satellite, which I was involved in. And then I want to revisit the main question and how well these advances conform with the competing secular and religious worldviews, particularly assessing strong claims by some popularizers of science, including Stephen Hawking himself. So let's start with Stephen Hawking. And I've got my pointer here. With whom this city is well acquainted. More technical problem. I've got the controller here anyway. And so, and we're rightfully very proud of Stephen as well. He passed away 5 years ago in March, which was a sad event. Especially for family and friends and colleagues who knew him well. But also there was a notable outpouring of public grief and much coverage in the media. Stephen made singular contributions that transformed our understanding of black holes and the Big Bang, despite all the odds being stacked against him right from the beginning. But his fame went far beyond the scientific community, as we can see, because he combined this with his hugely popular science books and lectures, together with his own story of triumph over adversity. It was a narrative that really inspired millions. I was privileged to know him personally, first as a PhD student, but then as a colleague for over 30 years. Those who saw his remarkable character at first hand saw the tenacity and determination with which he faced daily life, along with his ability to see the lighter things of life, with his great sense of humor, despite his difficult circumstances. When not traveling the world, he was always in his office at the Department of Applied Maths and Theoretical Physics, and he even struggled back into work in the last month of his life. Stephen's laser focus was always on tackling the really big questions about our universe, and his work keeps on giving and generating breakthroughs decades later, as Kip Thorne said about him. He gave answers to several foundational questions, scientific questions, which include, did the universe have a beginning in time? To which the answer is yes. And it's relevant to this talk because Stephen's cosmological singularity theorems, initiated during his PhD research, established mathematically that general relativity required that there must have been a Big Bang singularity in the past. This interest led to a collaboration with Roger Penrose, which culminated in the important Hawking-Penrose singularity theorems in 1970. And he would surely have shared the Nobel Prize in 2020 with Roger. Are black holes unique? And the answer is yes, because in 1971, Stephen made pivotal contributions to the famous uniqueness theorems for black holes, along with other people, but showing that they could be described just using two numbers, the mass and the spin of the black hole. Do we know what happens when black holes collide? Yes, Stephen introduced the concept of the black hole event horizon, and his area theorems should soon be confirmed by LIGO-Virgo, the sort of gravitational waves experiment. So these area theorems refer to how black holes merge together. Do black holes live forever? And the answer is no. And this was his really major contribution in 1974, which was the discovery of quantum radiation from the black hole horizon, known as Hawking radiation. And this brought into contact the two great revolutions of the 20th century physics, quantum mechanics and general relativity. And this led to Hawking's famous black hole information paradox about what happens when a black hole evaporates eventually through this emission process. And this remains a key touchstone in the quest to unify physics, general relativity with a theory of quantum mechanics known as quantum gravity, otherwise called a theory of everything. At this stage, Stephen turned his attention back to cosmology and asked, can we explain where all the galaxies in the universe come from? And the answer is yes. In early 1982, Stephen proposed that during a period of very rapid expansion of the universe called inflation, random quantum fluctuations would generate the primordial seeds required for galaxy formation. This is Hawking radiation from the cosmological horizon instead of the black hole horizon, which he had investigated previously with Gary Gibbons here in Cambridge. Later that year, Stephen called all the people working in this field together for a famous workshop in Cambridge, and out of this emerged the theory of inflationary fluctuations, which now are an integral part of the standard cosmology, with the predictions from that theory confirmed by satellite observations of the cosmic microwave sky. So the final question is, can we understand the origin of the universe itself? And the answer is maybe. Stephen's most daring intellectual project was his ambitious proposal that the universe has no boundary. This theory of the quantum origin of the universe, developed mainly with Jim Hartle, remains a work in progress and one on which he kept shining a light till the end of his life. Indeed, very recently, there's been a popular book about it by his collaborator and former student, Thomas Hertog, called On the Origin of Time. And, but there's, this is a problem that hasn't really been solved, and that there's a general view that the jury is still out on this particular issue. And that's fortunate for the rest of us, because it's good that Stephen's left some open questions for us to still address. Generally, Stephen's best known for his work on black holes, but in fact, he was a leading cosmologist, and about 60% of his papers were on cosmology. And in the 1980s, when I arrived from Australia here to work with him, he was in a decidedly cosmological phase. And he said his work at the time on the no boundary proposal, which is this last bit here, was the culmination of the book he wrote, A Brief History of Time. And this sold millions and catapulted him into instant celebrity. Now, as a scientific celebrity, Stephen also became a guru. And so he was unafraid to apply his common sense more widely and pronounce on matters well outside his area of expertise. His posthumous book, Brief Answers to Big Questions, provided a good example of this. It's mainly a compilation of popular lectures, and in it Stephen warned about the dangers of artificial intelligence, climate change, the need for space travel, and of course he discussed the existence of God and the beginning of all things. So Stephen's widely identified as an atheist, and as he says in the quote here, I think that it's important for scientists to explain their work, particularly in cosmology. This now answers many questions once asked of religion. His line was that cosmology now removes many of the superstitions associated with religion from the past. And naively, it fits into the picture that science has replaced God. But I would actually argue that Stephen's position was much more nuanced than that. In A Brief History of Time, Stephen concludes that if we do discover a complete theory, it would be the ultimate triumph of human reason, for then we would know the mind of God. Like Einstein, he imbues the quest for the laws of physics with a special significance. The theory of everything represents absolute truth. As he repeats in the Big Questions book, you can call the laws of science God, if you like, but it's not a personal God you can pray to. So the central question doesn't seem to be whether there is some prime cause or structure that defines, even creates the universe. Instead, we're left asking questions about the nature of the God of the new physics, whether this God is personal or impersonal, immanent or transcendent. In this regard, Stephen's views were very similar to Einstein, who believed in a sort of God, and I quote, who reveals himself in the orderly harmony of what exists, not in a God who concerns himself with the fates and actions of human beings. While this may not be the same as a traditional Judeo-Christian view of a transcendent God, it's not quite as far away as you might imagine, with this elevated view of absolute truth seemingly being a halfway house to theism. Anyway, the irony is that the Hawking family asked me to help with this book launch here. And so I was called up by the BBC London for a radio program on a Sunday morning. And the producer said they wanted me to explain why science meant we no longer needed to believe in God. And well, I told the producer that actually I didn't agree with Stephen's arguments on this point. So to which she replied, all the better, you know, we like controversy. So I went on the program, and during the program they had a live referendum on whether God existed or not. Anyway, you might be asking yourself at this stage, on what grounds could I have the temerity to disagree with my much more distinguished supervisor? Because we all know that students are not greater than their teachers. So rather than taking my word for it, though, I'm going to appeal to an alternative higher authority. And let's take a quick look at another preeminent theoretical cosmologist of the 20th century, who's George Lemaître. He's in fact Monsignor George Lemaître, and he's probably the greatest scientist, well, some of you have never heard of. And in 1923, he came to St. Edmund's College in Cambridge, and he worked with Arthur Eddington as a graduate student, where he learned about general relativity. He went on to do a PhD in astronomy at MIT in the other Cambridge, before returning to become a professor of physics at Leuven University near Brussels, maintaining his links with Eddington here in Cambridge throughout this time. Lemaître was the first person to both derive and explain the physical concept of an expanding universe. That there was a Russian Friedman who had independently written down these and other mathematical solutions, but hadn't really developed them in any way. Lemaître's 1927 paper is without doubt one of the most important in the history of cosmology. Although he published it in an obscure journal, his work was known to the great figures of that time, including Einstein and Eddington, who subsequently arranged for the paper to be republished in English. And later in 1931, Lemaître was the first to explicitly propose the hot Big Bang theory, the idea that the universe emerged from a primordial fireball, which he called the primeval atom. He had many other important ideas, including some of a speculative nature about the quantum origin of the universe, but also about dark energy, the cosmological constant, which has been observationally confirmed only relatively recently. Given that Lemaître was also a Roman Catholic priest, it's rather appropriate that he's called the father of the Big Bang, which is rather a weak pun, I know. So he was a founding member of the Pontifical Academy of Sciences, and in 1960 he became the president. Now, surprisingly, he took a rather, not surprisingly, he took a rather different view about the relationship between science and religion, declaring that they were not in conflict, nor that the latter had been superseded by science. His contention was that all truth derived from the same one source, God. So he affirmed the views of people like Francis Bacon or Thomas Aquinas, going back to the early church fathers, who used the metaphor of two books of divine revelation, one nature and the other scripture. Lemaître said, and I quote, "I was interested in truth from the point of view of salvation just as much as in truth from the point of view of scientific certainty. It appeared to me that there were two paths to truth, and I decided to follow both of them." Somewhat surprisingly, Stephen Hawking also accepted the invitation to become a member of the Pontifical Academy of Sciences, and he received their gold medal in 1975. At one of their Vatican meetings in 1981, Stephen introduced his famous no-boundary proposal for the quantum origin of the universe, in a way taking forward Lemaître's ideas about the primordial atom. In fact, I went to a conference in Rome with Stephen in 2016 to celebrate the life and work of Lemaître. I was very pleased at the event to meet a cardinal for the first time, but of course Stephen met the Pope. So let's focus back on the cosmology. We all now know that we live in an expanding universe, and as I mentioned earlier, this was a huge revolution in our understanding of the universe, and that Lemaître had deduced this from Einstein's theory of general relativity. If the theory was correct, then there would be no static universes. They all had to be dynamical in some way. The universe had to uniformly expand or contract, with the galaxies obeying a simple law, which stated that the velocity at which they moved apart was proportional to their distance apart. So this is known as Hubble's law, following the general principle that no scientific discovery is named after its original inventor. Lemaître then used the best redshift and distance observations that were publicly available at that time, including data from Hubble and Slipher, to estimate the rate of this expansion, this Hubble constant. 2 years later, Hubble published similar results, but now with additional better data. So let me just emphasize, here's a little montage of the expanding universe. That's how it goes. And here is Hubble And here's Lemaître's data set on the right and Hubble's on the left. Okay. So let's emphasize the extent to which Lemaître's evolving and expanding universe was an unexpected development at the time, and indeed a very unwelcome one. If you put an expanding universe in reverse, okay, as you go backwards in time, everything crunches together into a higher and higher density state, ending up with a big bang at a finite time in the past. In fact, it ends up being a singularity in general relativity, which means a state of infinite density. This essentially implied a beginning in time for our universe, because you can't project a singularity to earlier times. But this was an enormous conceptual leap that generated a great deal of antipathy and suspicion. In 1927, Einstein said to Lemaître, "Your work is mathematically correct, but your physics is abominable." He accused him of defending church dogmas, while others claimed he was introducing creationism. Eddington said, "The notion of a beginning in time is repugnant to me." So why was this so controversial? Well, ever since the first inquiries of the pre-Socratic philosophers, it had always been assumed that our universe was eternal and cyclical. Parmenides set out dual arguments for this, stating first that nothing comes from nothing, and secondly, the why not sooner paradox. That is, what would have driven the universe to appear at a particular time rather than earlier or later. This Greek view prevailed in every previous picture of our universe, whether it was Ptolemaic, Copernican, or Newtonian. All of these had existed forever and implicitly avoided the problem of a beginning in time. Even Einstein had tried to construct a static universe within general relativity, though Lemaître had shown it didn't work. Einstein's static universe wasn't static, it was unstable. On the other hand, the Judeo-Christian tradition was almost unique in violating the principles, these two principles. First, creation ex nihilo, out of nothing. Saint Augustine was a particular advocate of this interpretation. And secondly, to avoid the Parmenides argument, he proposed that time also began with the creation, so that God stands outside what appears to us the sort of inexorable flow of time. So now you can understand why Lemaître's expanding universe caused such consternation. In response to attacks on his model, however, Lemaître was very careful to disavow any claim that his scientific theory favored his own theological beliefs. He wanted his theory to be judged on its scientific merits alone. He was genuinely surprised himself at his scientific discovery. Eventually, by 1933, the evidence was mounting, and Einstein came around to the idea of an expanding universe. And so both Lemaître and Einstein did a lecture tour, as you would, around the US. And after Lemaître's lecture at Caltech, Einstein was reported to have said, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." So, despite, however, this observational evidence for a beginning in time, resistance continued to the idea. The hot Big Bang model remained deeply unpopular, and very few papers were actually written about it, notably in the 50s and early 60s. Instead, alternative cosmological scenarios were developed, which had expansion but avoided a beginning in time, such as bouncing universes, continuing on through some eternal cycle of birth and death. But the best known competitor was the steady state theory developed by Fred Hoyle, Hermann Bondi, and Tom Gold. In this model, Einstein's theory was modified by somewhat arbitrarily adding a source term to the equations. And this now new input meant the universe expanded through a process of continuous creation. The universe would apparently exist forever in this steady state. Now, the argument can be made that this model was much more motivated by metaphysical prejudices of its proponents than by scientific necessity or any empirical data. Quite unlike Lemaître, Hoyle freely admitted his bias by later noting that he had fundamentally a Greek worldview fixed in his mind ever since he read Homer. Classical scholars, he claimed, would recognize the motivation behind the steady state theory as in essence an expression of Greek theology. In fact, he said, without a beginning in time, it did not encourage a Judeo-Christian conception of creation by an external God. And this is not to mention Herman Bondi's strongly held humanist views. So it's clear that cosmology is more susceptible to this failing, that researchers can select the scientific models to harmonize with their own particular metaphysical prejudices, especially if there's no data available to contradict these strongly held views. The trouble from Hoyle's perspective was that his model was actually very susceptible to falsification. And this came through the discovery of the cosmic microwave background, a relic from the initial Big Bang fireball, which proved to be entirely incompatible with the steady state model. So Bondi and Gold soon abandoned ship and left Hoyle to carry on the fight alone for the model. But Hoyle's convictions were such that the theory must be right, that he went to embarrassing lengths to try and harmonize the two. And a second front against the steady state was also launched by Stephen Hawking, who pointed out the mathematical inconsistencies in the model. So the steady state model in the end proved to be a miserable failure, driven by presuppositions that could only be overcome by the most overwhelming data. It wasn't just the expansion of the universe that was required, it was also the measurement of the cosmic microwave background. And so this is certainly a lesson that we should be wary of those who construct systems of the world by taking their starting point in their own creeds, as the French astronomer Duvalier noted. So back to the beginning in time, Stephen Hawking had something very deep in common with Lemaître at an early stage in his career, because his PhD thesis submitted in 1965 was entitled Properties of an Expanding Universe, and in it he established mathematically Lemaître's assertion that the universe had a beginning in time. Under reasonable assumptions about the matter content of the universe, general relativity implied there must have been an initial singularity, the Big Bang, when time began. I mean, more formally, this is known as geodesic incompleteness to the past, and it essentially implies the incompleteness of the laws of physics in a way, because this infinitely dense initial state must indicate their breakdown in some way. So in one fell swoop, Stephen's work wiped out a whole genre of alternative cosmologies purporting to compete with the Big Bang, like the cyclic and bouncing universes previously mentioned. Again, there was a lot of initial opposition to this unwelcome conclusion, particularly from Soviet physicists who, for ideological reasons, preferred an eternal or cyclic universe in order to support the ongoing triumph of the proletariat or something like that. But as Stephen remarked afterwards, you can't really argue with a theorem. So, but from a personal perspective, this left Stephen with an enormous conundrum. He'd unwittingly confronted the scientific community with a huge mystery of the initial state of the universe. Even in his PhD, he said, it is one of the weaknesses of Einstein's theory of relativity that although it furnished field equations, it does not provide boundary conditions for them. He also bemoaned the fact that during his PhD work, he'd undermined the steady state theory that did not have a problem with the beginning in time. The irony is that he then devoted a large proportion of his subsequent career endeavoring to solve the problem he'd created. And just as an aside, I note that these singularity theorems have been examined in other contexts, for example, with different sorts of matter, looking at whether or not they are robust. And indeed, in an inflationary universe, it appears that you can't extend the universe infinitely far into the past. There is still an argument for a beginning in time. So let's move on to the quantitative observations of our universe, which have turned Lemaître's Big Bang hypothesis into an established and verified scientific theory we now call the standard cosmology. By far the best evidence for the Big Bang over the past 50 years, and the most quantitative information has come from this cosmic microwave background radiation. And about 14 billion years ago, the universe began with a gigantic explosion, with every particle flying apart from every other particle, and left over from this primordial fireball is relic radiation that's been stretched by the expansion of the universe to become a background of microwaves and radio waves today. So the microwave background radiation was released when free electrons and nuclei first formed atoms. So at that point, the universe became transparent, and then the photons propagated freely, without bumping into anything else up to the present day. And so when we look at the microwave background backwards in time, we're looking at a photograph of the universe, a snapshot of the blueprint of the universe 300,000 years after the Big Bang, okay, before any large structures and galaxies or other things were present. So we're looking at the initial state of the universe. That's why it's such an interesting area to study. Okay, so this was discovered in 1965 by Penzias and Wilson at Bell Labs, serendipitously. They weren't actually looking for it, and it was only told to Lemaître somewhat later, when he was very ill. In fact, I think it was only 3 days before he died that he learned that the cosmic microwave background had been discovered. And he's said to have remarked in response, "I'm happy now. We have the proof." Okay, so there was just uncertainty about what sort of universe we lived in until this major event, 1965. Okay, so the story of the microwave background is really a story of the triumph of 3 satellites. There's the Kobe satellite in 1993, which first detected this unambiguously across the sky. It first detected the fluctuations in this background across the sky. So that was the first indication that the idea of inflation was actually working. There were these little fluctuations in this. Then, so that was a very qualitative discovery for which Smoot and Mather received the Nobel Prize. But subsequently, the WMAP satellite, this really marked the transition of cosmology from speculation to a truly precision quantitative science. And as John Bacall says there. And so we finally had a very precise picture of these little quantum fluctuations. And here they are. And the Planck satellite went another stage further with perhaps an order of magnitude more information. And you can argue that, at the time, 90% of what we knew about the universe was in this map here that Planck had identified. And it's an instrument, European Space Agency satellite, which looked at several frequencies and put these together, removing the dust and other contamination from the galaxy and elsewhere, and put it all together in this map of what are meant to be the primordial fluctuations left over from the Big Bang. And that's what it looked like in 2013. This is the projection, by the way. If we did a projection of the sphere, we've got a full sky picture of the universe. And this is the projection that the Earth would look like. Anyway, here's 2013, 2015, these are the data releases, and 2018 was the last one. And so the last papers from Planck were in about 2020, although it's a sort of decadal survey, so it's not really going to be superseded for another 10 years perhaps, but lots of new experiments are coming along. And so what we're interested in quantitatively are these little fluctuations. And so what is the power on particular length scales? So here's 20 degrees. And if you look at the picture, actually the dominant power is actually at 1 degree. It's a sort of size of my thumb. You can see all those lumps there. And so you can turn that into a power spectrum. And this is what the data looks like when plotted in this way. You can see most of the power is at about 1 degree there. And then there are these sort of oscillations like this on different length scales. And so these oscillations here are really, the universe processing what was a very simple signal coming from inflation. This quantum fluctuations had almost no features in them at all. And this is how the hot gas was oscillating during the history of the universe. And from this data here, one can derive the cosmological parameters and very interesting things about our universe. So let me just describe very quickly what inflation is all about. Inflation is the idea that tacked onto the beginning of the hot Big Bang, there was actually a very fast expansion like this. This was suggested by Alan Guth at MIT, where I worked for a while. And but Stephen Hawking recognized that if the universe was expanding very rapidly like this, then we would have a cosmological horizon. And a cosmological horizon was like a black hole horizon. And that meant that you have Heisenberg's uncertainty principle in operation. If you restrict delta x, then you have this, the position, then you have uncertainty in the momentum. And so you create these quantum fluctuations. And here's a sort of simulation of the creation of these fluctuations. So what they are, they're created on microscopic scales, but the expansion is so rapid that then they become very large and they get imprinted into the fabric of space-time. And later, in the later stages of the universe, when gravitational effects become important, they recollapse and become galaxies. Okay, so I'd better rush on here. I would have told you a little bit about my own interest, which is trying to go beyond the power spectrum, beyond correlations at 2 points, to look at correlations at 3 points. And the intention here is to look for models that might give us a clue about inflation. Inflation is so extrapolated back into the early universe that we don't really know the correct theory for it. We just know that this is a good mechanism, and the predictions from it are very close to what we see. And so, but are there extra clues, perhaps about a model with extra dimensions or extra fields, maybe the presence of cosmic strings and things like that? But I won't bother you with my particular interests. Let me just point out that this picture of these ripples in space-time, which produce this power spectrum here, can then be compared to models, mathematical models, with different parameters. And so, for example, here we're varying the amount of dark matter. And if you stop at the appropriate match with this power spectrum here, you can estimate how much dark matter there is in the universe, and you do the same across all parameters. And so that brings us to our standard concordance model, which describes the universe to almost sub-percent precision now. You know, remember, we didn't even know things to a factor of 2 when I was a graduate student. And so so we know that 5% of the universe is visible matter, ordinary matter that we're made out of. Then there's something mysterious, cold dark matter, about a quarter of the universe, and about 70% is made up of dark matter. So here's the sort of recipe of the universe, our old universe, and there's the Hubble expansion rate, how fast we're expanding. There's a lot of talk in the media. Sometimes there's a great crisis in cosmology because there are small differences emerge in the Hubble constant between different ways of measuring them. And you know, the suggestion was that if you take late time measures of the Hubble constant using supernovae, so that's in recent redshift, compare it to the cosmic microwave background, which is back at a redshift of 1,000, then maybe there's some sort of new process between then and now, which requires new physics. But in fact, it's most likely to be some sort of systematic effect, because other measures of the Hubble constant at late times provide great consistency with the Planck result. So I won't bother you with that. I'll press on to what the standard cosmology looks like. If I go back to that. So we have the formation of the light elements in the first 3 minutes. About 400,000 years after the Big Bang, the cosmic microwave background is released. We get our first galaxies, and then eventually the universe starts accelerating about 11 billion years after the universe gets taken over by a cosmological constant or dark energy, as predicted by, well, as studied at least by Lemaître. Then going back in time, we're looking at the first, into the first hundredth of a nanosecond is the sort of energy scales being studied at the LHC in CERN. And then here, this dramatic extrapolation back to 10 to the minus 35 seconds is where we think inflationary processes are happening. But there's this irreducible problem that we don't know about the origin of the universe itself, because we need a theory of quantum gravity. And it's very, very difficult to test such a theory at such high energies. And so this is the, we don't know what that theory is. And so that's a theme of what I'll be talking about as we go along. So there are these sort of three epochs. This a very reliable standard cosmology since 100th of a second after the Big Bang. There's this intermediate scale where we actually know the theory, the standard model of particle physics. It's rather difficult to calculate things, however. And then finally, there's this sort of imaginative area here in the early universe where we're getting some insight from inflation. Okay, so there we are. Right, so now I can see my time is running out, but so I'm going to skip some slides here and get to my general conclusions. But you know, this is the subject of what could be another talk. I'm not inviting myself, but so about the anthropic principle. We actually live, you know, it's a wonderful, rich tapestry, this story of the history of the universe, but we actually live in a very special universe where all the sort of fundamental constants are essentially fine-tuned such that life is possible. If you meddle with any of them, pretty much, you mess up the picture that we have. And many books have been written about this problem, the anthropic principle. In fact, Stephen Hawking himself wrote papers about it with his colleague Brandon Carter here. And so now there are many books about it, including one by Martin Rees. And the fact is it's sort of inexplicable why our universe is so special. And so there are various ideas about why this might be the case. And the idea of an inflationary universe provides one mechanism by which you could explore if other universes were possible, you could change the laws of physics, then inflation allows you to explore other possibilities. And, popular, for a theory of everything is string theory or M theory. And it turns out that these have many possible vacua, different types of universes that could be produced. So perhaps 10 to the 500 possible universes, types. And so you put these together and you get this idea of a multiverse, okay? So it's a reasonable extrapolation. Of course, there's no evidence for it at all, but it's a fun thing to explore. So the idea is that you solve this fact that we live in a very special universe by the fact that if you explore all these possibilities, then we will live in the one where life is possible, where all the parameters are such that they overlap correctly in this particular sub-universe. In fact, I don't believe that actually solves the problem, because in fact you could imagine a multiverse where these things didn't overlap and there was no life at all. But let's leave that aside for the moment. I just want to emphasize that we have now a very standard cosmological model, which is very reliable, quantitatively tested. And I want to distinguish that from metacosmology, okay, these sort of ideas of the multiverse and the quantum origin of the universe, because we don't yet have a quantum gravity theory. All right. So, are all these developments that, where we understand the evolution of the universe so much better now than Lemaître's time, do these have a particular implication for, whether or not these big questions about our existence? So that's a useful context in which I want to draw this to a conclusion by discussing some popular books by Stephen Hawking and others, claiming to offer new insights in this sort of science and religion domain. And the first is the Grand Design here by Hawking and Mlodinow, and another is a Universe from Nothing. And I've already mentioned this one on the Origin of Time by Stephen's former student. The first two books here argue strongly that our understanding of the origin of the universe is now so complete that there's no room left for a creator. As Stephen said to CNN when promoting the book, God may exist, but science can explain the universe without the need for a creator. And here's another headline. Of course, the books start on a rather different tack, acknowledging the shortcomings that I've summarized already in the standard cosmology, such as the apparent fine-tuning of the laws of nature, but pointing out that this is not easily explained. And, it indeed raises the natural question of why it is that way. But ultimately, Stephen says there's no need for a grand cosmic designer. The appearance of all this fine-tuning and order is an illusion of design, and it can be explained by a landscape of possibilities with all these multiple universes. And as I've explained, and echoing a similar theme, Krauss points out that the universe could have been created spontaneously out of a vacuum or out of nothing, using his words. So as an aside, let me point out that these ideas now pervade popular culture, even though the worldview they offer is not particularly attractive, especially in terms of eschatology or our future prospects. The projections for our universe are really Lemaître's slow fading of the suns, that is the heat death of the universe, in which continuing expansion will ultimately create vast frozen landscapes of emptiness. As Richard Dawkins himself admits, if you think that is bleak and cheerless, too bad. Reality does not owe us comfort. So the vaguely formed God of the new physics seems to offer us little hope and only the illusion of design with no ultimate meaning or purpose. And it seems only to get worse with the multiverse. Despite the lack of any empirical evidence, Hollywood has adopted the multiple universes, you may have noticed. So I felt it was my duty on recent long-haul flights to watch the latest multiverse movies so that you didn't have to. Okay. And so here's one, Doctor Strange and the Multiverse Madness, and also the Everything Everywhere All at Once, and which got 7 Oscars somehow. These movies are characterized by fast-paced, somewhat arbitrary plots, sowing a great deal of chaos and confusion, just like the speculative theoretical physics models on which they're based. Okay, but anyway, I won't comment further on that. So back to the topic at hand. Okay, so which is some sort of critique of these theories about the origin and how they're presented to the public. Because for the lay reader, it can be challenging to assess the merits of claims of popular books, because the authors make it difficult to distinguish between established cosmological facts and speculative extrapolation. In fact, Stephen Hawking's Brief History of Time suffers from this pattern of writing. The first 2/3 is about well-established advances in the field, many of which have been verified observationally. But then the last third is about his own no boundary proposal, and which is much more speculative, and the reader is none the wiser of the transition from tested scientific theory to this realm of metacosmology. However, for those more familiar with the field, this is fairly easy to identify the difference between what's established science and what's speculative. So it's quite easy to make a negative critique of the rather overblown conclusions of these popular books. So first, the cosmological models describing the origin of the universe have to be built on a key ingredient, and that is a theory of quantum gravity, okay? Something called the theory of everything. And this is needed because Big Bang models must extrapolate to the highest energies imaginable. So we must be sure that any approximations that we're making mathematically are made and kept under control. This is otherwise known as ultraviolet completion. While there are some plausible candidates for theory of everything, like string theory or M theory, we don't actually know which is the correct quantum gravity theory, because none of these candidates have ever been scientifically verified or tested. And unfortunately, it seems clear that this remains a far-off prospect, even if you believe that the theory of everything can be deduced a priori without empirical evidence. In Stephen Hawking's inaugural lecture in 1979, he said we would know the final theory of everything in 20 years. After a further 20 years, he said we would know it in another 20 years. But after another 20 years, he, in this final book, he said we would know it by the end of the century. In fact, he qualified this further and said, now I think the wonder of discovery will continue long after I'm gone. The second point is a consequence of this vital missing ingredient. It means that we have very little confidence about the models for the origin of the universe, because ultimately they contain approximations to quantum gravity, as I said, that are optimistic at best and probably are going to be found to be unreliable. So this picture being presented in all these popular books is undoubtedly speculative, and it's incomplete. There really is no closed scientific framework available for the origin of the universe for them to boast about, irrespective of their aspirations to find this. In the face of robust unknowns like fine-tuning, the authors leave behind empirically tested science and delve into metacosmology, including adding things like the multiverse. When making apparently definitive statements about the quantum origin of the universe, they're in fact disguising a leap of faith that is somewhat akin to a religion in many ways. The reductionist or materialist does not have a complete scientific picture at hand. Their enthusiasm to be anti-religion has itself required a step of faith to shore up their own edifice, and so they've ended up with some sort of pseudo-religion themselves. So the third critique is that a lot of category errors are being made to manufacture an apparent conflict between science and religion. And this typically involves creating religious caricatures and then shooting them down, particularly the idea of the God of the gaps. Lemaître was adamant about this point, stating that he had too much respect for God to reduce him to the role of a scientific hypothesis. He, after all, is the creator and sustainer of all that is. He can't be shoehorned into the first nanosecond of the Big Bang. Another example of the false dichotomy is created by juxtaposing God against a multiverse. A theist is already comfortable with a large universe, so a few more aren't going to be a problem, and nor are they any more or less dependent on their creator. On the contrary, the boot is on the other foot, in that it is really the reductionists who require additional ingredients to fill the gaps in their own scientific understanding. In other words, to close the circle of their speculative picture. Fourthly, there are a lot of dubious claims from a philosophical perspective, for example, the creation from nothing, which is meant to be, which is actually an initial vacuum state, which is certainly not nothing. But I'll move on from that. So these additional speculative elements required to put forward an origin theory for the universe, combined with a number of category errors, do seem to provide remarkably shaky foundations for the reductionists to make confident assertions about the existence, or rather the non-existence, of a cosmic designer. So at this point, I'm kind of running out of time, I see. So I hope my chair will indulge me a little to get to the conclusions. I've already alluded to the idea that, in fact, it's possible to interpret this elevated quest for absolute truth in the laws of nature as really some sort of halfway house to theism. And if we sort of analyze Stephen's argument about whether or not we can pray to this God, it's a sort of discussion about the nature of the first causes of the universe, whether this God is just a mathematician, or rather a mathematical structure, or whether there is more rounded personality and evidence. Is God immanent, impersonal, and silent, or is God personal and multi-layered, somehow transcending the laws of physics that govern the universe? Stephen has chosen the impersonal over the personal, but the very vague outlines offered by cosmology aren't really going to settle this question anytime soon. But a different answer to this question means that the subject can be approached from a different perspective. So what's the appropriate Christian response to these developments in modern cosmology? Well, fortunately, John Polkinghorne, a former chair of mathematical physics in my own department, who became an ordained Anglican priest, spent a great deal of time thinking about these issues from a theoretical physics perspective. So I'm unashamedly going to lean on some of his thoughts in my final remarks now. So how do we understand the universe? Well, this happens at several levels, and the first response that it offers a reason why we can make sense of what we've learned about it, why there is coherence and intelligibility, and why our knowledge continues to advance. We're reminded of Einstein's dilemma when he said the most incomprehensible thing about the universe is that it is comprehensible. Or Eugene Wigner said the unreasonable effectiveness of mathematics. this progress should not be a surprise from a Judeo-Christian perspective, because the intelligibility of the universe, its orderly structure and its fruitful potential would be expected, because it somehow reflects the consistent character of the intelligent God who created and sustains the universe. So reinforcing this, humanity is also meant to share the image of the Creator, thus giving us further reason why the world is comprehensible, why we can aspire through science to read the handwriting in the book of nature. Lemaître expressed it in this way when he said, "A one who gave us the mind to understand him and to recognize a glimpse of his glory in our universe, which he has so wonderfully adapted to the mental power with which he has endowed us." The second response is one of humility. And this is because we're really living in a wonderful universe, as you've seen from this rich tapestry on the right here. And we're learning new insights more or less every year. And there's so much more to learn. We've only mapped a small fraction of the universe so far. And it's a universe of great antiquity, 14 billion years old, but the size of the universe is even more impressive. I mean, if you compare yourself to dust particles in this hall, you're vastly exaggerating your own importance. And in fact, the Earth itself is 1,000,000 billion times smaller than any speck of dust in this hall, relative to the size of the room. And as we've learned, the anthropic principle, it isn't just the magnitude of the universe, it's also its intricate detail. And the wonderful fireworks display of the universe, which makes up cosmic history, is very finely tuned between competing physical mechanisms to allow the possibility of our existence here on Earth. And all this potentiality was there, built into the physical structure of the universe right at the very beginning of the Big Bang, long before Richard Dawkins was ever conceived of. It's indeed a very special universe, and it almost seems, as Stephen points out in his book, if there is some sort of grand design. And the psalmist says something like, "The heavens declare the glory of God." I think I've got it there. And even though they only had a very limited understanding of how far away the stars of the Milky Way are, let alone that there are galaxies far beyond that, hundreds of billions of them, even trillions. And of course, the Christian faith is about a personal God who's much more than just governing the laws. It's about a personal God who's mindful of those who inhabit his universe. And so he even cares about us. And that's just the beginning of the Christian perspective, which encompasses a much broader story of engagement with mankind in space and time, reaching its climax in the Son of God who dwelt among us, and ultimately in the cross. There's a complementary grand design at a personal level with a God who you can meet and pray to. That's the other quest for truth in salvation history that Lemaître spoke about. So the Christian perspective has a long tradition, being associated with the birth of modern science, with Galileo and Newton, as well as developments like electromagnetism with Faraday and Maxwell, and as we've seen with the beginning of the universe itself with Lemaître. These great scientists believe themselves to be following in the footsteps of the Creator. Maxwell summarized this motivation when he said the following: "I think Christians whose minds are scientific are bound to study science, that their view of the glory of God may be as extensive as their being is capable." So what about the alternatives? Especially, what about the reductionist picture presented by Stephen Hawking, Lawrence Krauss, and others? Are their claims really a necessary response to improvements in our understanding of our universe? And does it offer a more coherent frame in which to comprehend the amazing universe in which we live? I don't think their arguments are compelling. As we've seen, it's built on shaky foundations and misunderstandings, and their vaguely outlined God of the new physics offers none of the usual reassurances about meaning and purpose. So let me just finish on a more positive note with a final slide of the two great cosmologists at their blackboards, one from the beginning of the 20th century and the other from the end. As the quotes indicate, they shared so much in common about the wonder of the discovery, as well as their ultimate quest for scientific truth. And together they have transformed our understanding of the beginning of all things. And I think I've well run over my time now. Thanks very much.
So thank you, Paul, so much. Wonderful tour, grand tour that we've had of standard cosmology and metacosmological ideas, and some thinking as well about a Christian response to some of that, and how we might respond to what the science is telling us about those early stages of the origin of the universe. And I hope to see you again at a Faraday event soon. Thank you, Paul.